This video is produced by Sammy and
Kevin Burgess
for byInquisition Press to support the workbook Sophomore Organic Chemistry 2 by Inquisition, available from www.byinquisition.org.
Today we're going to talk about enols and enolates. Carbonyl compounds in general are so interesting because the carbonyl carbon is an electrophile, but by forming an enol or an enolate, we make the alpha carbon into a
nucleophilic center.
The mechanism of formation of enols is two steps. First, we protonate on the oxygen for an aldehyde or a ketone or an ester, and then deprotonate on the carbon to get the enol form. Protonate on the oxygen, deprotonate on the carbon to get the enol form. Imagine what would happen then if we take a ketone in deuterated acid. The deuterium would add to the oxygen, proton would be removed to form an enol, but if that enol was again deuterated on the carbon, we have substituted the alpha CH with an alpha CD. Every CH in an enolizable compound could be exchanged with deuterium. So in this molecule here, Sammy, how many CHs will exchange?
One.
And in this one?
Two.
1,3-dicarbonyl compounds enolize very easily. And one reason for that is when we form the enol, it's conjugated. 1,2-dicarbonyl compounds, they also enolize easily, but the reason is different. Formation of an enol relieves an unfavorable dipole-dipole interaction. So if we're asked to draw enol forms of the following for the 1,3-dicarbonyl, it's easy. We just form the enol between the two carbonyls, so we get that conjugation. For a keto ester, let's enolize the ester or the ketone. So
The ketone.
we can look at other functional groups. Even if they don't have oxygen, actually, we can still make enol and enolate forms. For an ester, it's obvious. For an amide, it's quite obvious. For this mixed anhydride, well, only one of the sides has an acidic CH, so that's the only side where it can enolize. For carboxylic acid, enolization gives us two OH groups on the alkene. For thioesters, we can make a nice enol form. Enolate formation is even easier to picture than enol formation because it's just one step. Push the electrons in from the base, deprotonate, and push two arrows, and the electrons end up on the oxygen of the carbonyl. If we protonate the enolate on the oxygen, we get the enol form. Methoxide and methyl acetate gives us the enolate, and we protonate that, we get the enol form. Sodium hydride and methyl propionate gives us a mixture of E and Z enolates, and when we protonate on the oxygen, we get E and Z enol form. Sodamide with a nitrile will give us that ketene imine anion. If I take a compound with an alpha chiral center on the enolizable carbon and another distal chiral center, and I enolize it and then protonate, I get a mixture of
Diastereomers.
Your stomach is very acidic, Sammy. And so if you take ibuprofen and it goes into your stomach and you form an enol form, we racemize. Now another interesting consequence of enolization is if I have a double bond that's not quite in conjugation with the carbonyl, we form an enol and then I protonate, but this time on the beta carbon, I would generate a keto form. This is interesting for vitamin C. Vitamin C has a carbonyl. Do you see an enol in vitamin C, Sammy?
Yeah, I do.
Yeah, it's a funny one. It's got a hydroxide on either carbon. If I protonate that on the alpha carbon, I generate a carbonyl in the beta position. In glucose, if we form an enol, then protonate on the C1, That shifts the carbonyl over to the second position and we form fructose.